Welcome to AI Pulse. Today, we are breaking down a massive performance breakthrough for local artificial intelligence. Ollama has officially integrated Apple's native MLX framework. This brings a colossal speed improvement for local large language models running on Apple Silicon, with users reporting inference speeds up to 2 to 7 times faster. As shown in the official XDA Developers announcement in Slide 1, if you are running models on a Mac, this update transitions local AI from a slow developer novelty into a robust, cloud-speed workspace. Over the next 10 minutes, we will walk through exactly how this integration works under the hood using a series of whiteboard diagrams and code resources. As shown in Slide 9, running local models is the future of sovereign engineering, so let's check out the architecture. Let's look at Slide 2, which illustrates the Unified Memory Architecture, or UMA, of Apple Silicon. In traditional computers, the CPU and GPU have separate pools of memory. Whenever a large language model runs, the system must constantly copy gigabytes of model weights from system RAM to GPU VRAM. This constant data transfer creates a massive bottleneck limiting inference speeds. Apple Silicon solves this by using a unified memory pool shared directly by both the CPU and GPU. The model weights are loaded once and accessed with zero copy efficiency. By optimizing for unified memory, the new Ollama engine allows the GPU to read model parameters directly, cutting out the copying bottleneck. To see the software behind this performance, let's examine Apple's official open-source machine learning library, shown in Slide 3. Apple's MLX is an array framework designed specifically for machine learning research on Apple Silicon, built by their research division. It features Python and C++ APIs that closely mirror NumPy and PyTorch, making it easy for developers to port models. Crucially, MLX features lazy evaluation, automatic differentiation, and dynamic graph compilation. By writing a dedicated engine on top of MLX, Ollama directly leverages Apple's own compiler optimization work, bringing native metal executions straight to local developers. Now, look at Slide 4, comparing the older Llama CPP backend to the new native MLX engine. While Llama CPP is an incredible project that brought local LLMs to the masses, it relies on generic CPU and GPU pathways that carry extra layers of abstraction. In contrast, Apple's MLX machine learning research framework is built from scratch specifically for Apple Silicon. It bypasses generic layers, utilizing specialized metal execution shaders that are custom-tailored to the hardware's cache sizes and registers. By compiling execution graphs directly into metal, the MLX engine extracts the absolute maximum performance from your Mac's graphics cores. To see how this speedup is achieved at a compiler level, let's examine Slide 5, which details just-in-time compilation in MLX. In standard deep learning libraries, operations like matrix multiplication, activation functions, and layer normalization are sent to the GPU as separate, sequential commands. This introduces significant dispatch overhead. MLX solves this using JIT compilation, which compiles and fuses multiple sequential GPU operations into a single, highly optimized metal kernel. By running the combined kernel in one pass on the GPU, MLX dramatically reduces memory read and write cycles, squeezing maximum throughput out of the unified memory bus. Slide 6 maps out the software stack of this native integration. At the top, developers run autonomous agents like Claude Code or Aider. When these agents execute tasks, they call the local Ollama client API. The API directs the request to the new Ollama MLX inference runner. The runner dynamically compiles operations and executes the model on Apple Silicon's GPU and neural engine. This direct, low-latency integration means that local agents get responses almost instantly. This real-time loop is critical for agent workflows, where a single task might require the agent to call the model dozens of times in a row. Another major advantage of the MLX integration is shown in Slide 7, which details support for advanced quantization formats like NVFP4. When running models locally, we must compress their weights so they fit into unified memory. Traditional quantization methods like Q4 reduce memory usage, but often degrade the model's intelligence and reasoning capability. The new NVFP4 format, specifically optimized for Apple Silicon hardware, provides a far superior balance. It achieves extreme compression while preserving the model's original accuracy. This allows developers to run larger, more intelligent models on entry-level Macs with standard memory configurations. Let's look at the actual performance benchmarks in Slide 7 when comparing the older Llama CPP back into the native Ollama MLX engine. The results are staggering. For Llama 3.8b, token generation speeds jump from around 35 tokens per second to over 72 tokens per second, representing a clear 2x speedup. For Mistral 7b, the performance climbs from 42 tokens per second to 85 tokens per second. In optimal environments, newer Mac Studio configurations see speedups up to 7 times faster, making local models run faster than cloud-hosted APIs. This performance boost is a game-changer for developer workflows. As shown in Slide 6, modern software development is moving toward autonomous agent loops. Agents like Claude Code plan their work, write code, run tests in local sandboxes, read the error outputs, and refine their scripts autonomously. These multi-step planning loops require constant, low-latency LLM calls. When each call is sped up by 2 to 3 times, the time to complete a programming task drops from minutes to seconds. Snappy local inference makes autonomous coding agents practical for daily development. This speedup also unlocks the true potential of local AI, which is data privacy. As illustrated in Slide 2, central cloud APIs require you to send your proprietary code, database schemas, and private API keys to remote servers. This introduces massive security risks and compliance hurdles under frameworks like the DPDP Act or GDPR. By running Ollama MLX locally, your data never leaves your Mac's unified memory. You get cloud-level speed and intelligence while maintaining a strict zero-trust posture, keeping your company's intellectual property completely secure from external data collection. The efficiency of Apple Silicon also makes it a highly cost-effective option. As shown in Slide 4, running massive models on traditional PC architectures requires purchasing multiple power-hungry discrete graphics cards, which is expensive and loud. In contrast, a single Mac Studio with unified memory can run 70 billion parameter models at highly usable speeds while consuming a fraction of the power. The combination of native MLX compilation and energy-efficient hardware makes Mac hardware the premier local workstation for running state-of-the-art AI workloads. Getting started with this new engine is incredibly simple, as outlined in Slide 8. First, download the latest version of Ollama for macOS. Next, open your terminal and run the command Ollama run Llama 3, MLX. Ollama will automatically detect your Apple Silicon chip, download the MLX-optimized NVFP4 model weights, and load them directly into your Mac's unified memory. Ollama then runs a local API server on localhost port 11434, allowing you to instantly connect your coding tools, terminal clients, or custom developer scripts. As we wrap up our review in Slide 9, the future of on-device AI is incredibly bright. The integration of native MLX compilation with unified memory hardware proves that developers do not need to rely on expensive, centralized cloud APIs to build advanced autonomous applications. Upgrading Ollama is a simple step that immediately doubles your local inference performance. Let us know in the comments which models you are running on your Mac. Don't forget to subscribe and follow Pulse AI Digest for daily technical breakdowns, and we will see you in the next video.